Good morning, guys. I'm just going to do a quick video this morning on three-phase distribution systems. We're going to be going through delta Y configurations and just building on some of the math that we're going to be using in this part of the course. Essentially what we're going to be getting into is three-phase RLC circuits, but at the start we're going to get into things bit by bit so we don't overwhelm you too much. So three-phase distribution systems, as they refer to, they have three phases. There's two different three-phase systems you can see. There will either be a Y configuration, which is going to look like that, and the way it looks like here, this could be a three-phase alternator producing that voltage, or it could be a three-phase transformer, so there'd be three individual transformers producing the voltage that you'd be using, or that can even be how a three-phase load ends up looking in a circuit. So this is a Y configuration, which would look like that, right? And then secondly, we would have a delta configuration, which would look like that. So this is delta. And Y. Okay. When we're going through and analyzing delta and Y configurations, there are a lot of differences between how the math is done. Primarily, how we go from our single phase values into our three phase values, and I'll break that down for you with the Y configuration first. So in a Y configuration, we look at, and if we were to look at this as a circle, and all of these windings were 120 degrees at a phase with each other. So 120 degrees, this one's 120 degrees, and this one is 120 degrees. So obviously I drew that a little off, but all three of them are 120 degrees at a phase with each other. If we notice on a whole, it's 360 degrees all the way around. The reason why this is, and the reason why we state that they're separated 120 degrees apart from each other, is that all voltage that you're going to be producing, or that is produced rather in North America, it doesn't matter if it comes from water or if it comes from wind, so that encompasses about probably 99% of how power is derived, is from a three-phase alternator. And this will be more the next topic we get into, but I'd just like to talk about it a little bit. So a three-phase alternator obviously looks, we gotta put our stator in here. Our stator is the external part of our armature, or external part of our alternator. Actually, I'll put these. So this will be just a basic example. I won't obviously put all the coils in here. So I've got three coils. This is going to be coil number 1, coil number 2 and coil number 3. In the center of our alternator is a magnet. And if you remember from intermediate theory B, there are 3 things that you need to produce voltage. If you remember the formula, EG, so that's your generated voltage, is equal to K, which is your conductors, which is a constant, phi, N. So K phi N. And phi, that should be more straight up and down, phi, or phi rather, is your magnetic field, and N is your speed or your relative motion. So what I need is, obviously I've got conductors. My magnet is going to have a magnetic field that's produced on the outside of that magnet, and I need relative motion or speed. So I need that magnet spinning round and round. So as we had talked about, 120 degrees apart, so my windings are spaced 120 degrees apart, and as that magnet ends up sweeping past those phases, so this would be phase A, B, and C, we end up, if we were to look at a sine wave, so right now the north is sweeping past that point, so it would be up here at that would be typically at 90 degrees in our sine wave. As it goes to move past, we would find that that sine wave would go down to 0 when we were perpendicular to those coils. As the south begins to come around, we would get our negative, and then it continue on with our positive as it came back around. And obviously that would continue to go, and we would get our 3-phase sine wave. As the north ends up coming towards phase B, I would end up finding, so we're 120 degrees apart, so this one here would probably be about here, and yeah, about that. We'd end up getting something like that, and then phase number, so that would be B, this would be A, and this one is 120 degrees past this one, so we would end up getting, that guy would probably start somewhere around here, and would come back like that. So when we refer to 120 degrees out of phase, it is with respect to this, that the magnet that's spinning around in the alternator, when it cuts through those coils to produce a voltage, those voltages happen 120 degrees apart. So when we end up doing all of our calculations, we need to keep in mind that phase number A, phase number B, or sorry, phase letter A, phase letter B, phase letter C, they're not all reaching their peaks at the exact same time. And therefore, if they're not being produced at the exact same time, we can't consider all of their voltages to be just added directly together. And I'll show you what this means now. So I'm going to draw my Y again. So this coil here, when the magnet whips past it, this little coil here produces 120 volts. Let's just say that. When it comes around, it produces 120 volts there. And when it comes around here, it produces 120 volts here. So in all three cases, it produces 120 volts. If these two values, if they were 180 degrees out of phase with each other, as we would see in a single phase line 1, line 2, if we did it as a vector, we would see this is our start point. We would end up seeing that we have 120 degrees, 120 volts, 120 volts, and these are 180 degrees from each other. We could add the vector sum of those two, and the vector sum of those two would be 240 volts. Okay? Because they're not 180 degrees out of phase with each other, but instead are 120 degrees out of phase with each other, we end up getting something that looks like that. And then if we were to take the vector sum of those two values, so the vector sum of that guy across here, we would end up finding that that voltage is 208 volts. And I'm sure you guys have seen that before. Any three-phase system, you're going to be working with 120 to 208, not the conventional 120 240 that you would see in a residential home. So anytime you see voltages that are set up in a Y configuration, with this could be 120 volts, this could be potentially 347. The value, so this is a phase value. If I go to look at the line value, so the line value, this is exactly like if I were to take a voltmeter and test from one side to the other. If I were to take a voltmeter to test those two, obviously I'm not going to be testing inside and looking at each phase if I'm looking at line value. So if I was to look at line value with my meter, I would go from this point here to my center point, and this guy, I'll make a note, this is called your star point. So that's your star point, is in the very center. If I go from lines, so this would be like line 1, line 2, line 3. If I go from line 2 to my star point, and this is where you would connect a neutral in a three-phase system, I would read 120 volts. But if I look at either line 1 to 2, line 2 to 3, or line 3 to line 1 with a voltmeter, I'm going to be looking at the combination of these two voltages, but they're not 180 degrees apart as we saw up here, they're only 120. So we end up finding that that voltmeter would end up reading 208 volts. One thing I want you to pound in your calculator just so you can see it is if we do 208 divided by 120, that gives you a value, which is a constant that you can use for all three-phase power supplies. So anytime they're in Y and you're looking to increase your voltage, and there is a thing with current when we get the delta delta, where this will also work. But the answer to this equation is how much larger the voltage will be from a phase value to a line value. So what you end up finding is that this is 1.73. All right, so that 1.73 is going to be the value you're going to use in order to go from 120 volts to 208 volts. So if you do 120 times 1.73, I think it's 1.732 is what it works out to, it will give you a value of 208 volts. The other thing that you can do is that if I take the square root of 3, the square root of 3 will also give you that value. So rather than having to think about 1.73 all the time, if you just remember to use that value of root 3, and we'll end up using this in our formulas, you can also get 208. So if you do 120 volts times root 3, it'll give you 208 volts. If you do 347 volts times root 3, you're going to end up getting 600 volts. So that's an important one to remember there. Okay, so voltages are always going to be root 3 larger. And if you're trying to remember that they are root 3 larger, if you always think of using a meter, and if I was going to, and if we look at this as an alternator or 3 individual transformers, and we put a meter across, always remember that there's 2 coils that are producing that voltage. And obviously we're not in a single phase system, so you can't just assume 240. But if you look and say, oh, my meter's measuring 2 different coils that are producing that voltage, then my value has to be a larger value. It has to be bigger. And how much bigger is it? It's root 3 larger, because those 2 phases are 120 degrees apart. So that's for voltage. And then I'll just do a little summary when I'm done here with this, with formulas. And then the other thing is looking at your current in the system. So, excuse me, if I was to look at a amp clamp, and I was to take an amp clamp and I was to put an amp clamp around that coil, well, what would that coil produce? So let's say the resistance on that coil is, let's say it's 12 ohms to make it easy. So 12 ohms is the resistance. If I wanted to figure out the current, (120 volts divided by 12 ohms is going to give you a current of 10 amps. If I took my amp clamp and put it on that coil, it would read 10 amps, right? If I end up moving out to my line value, notice how that's the exact same point electrically. I'm not adding any other wires to it. I'm not clamping on that one and that one. It's only one wire. So in Y, my current in the line is always the exact same as it is in the phase, because I'm not picking up another coil or another load in the circuit. Okay? So I'm going to erase that quick. So I'm going to go through the rules for Y and delta, and then I'm going to call that a video, because it is a fair amount just to start out and figure out. So in Y, in Y, we know that, and I'm going to put this as our voltage, but I'm going to do as E line. So our voltage in the line is equal to our E phase, which is our phase voltage, times root 3. Okay? If I have a phase value, it would be E line divided by root 3. That's very important to notice the difference. So if I'm going from a phase value to the line value, always root 3 larger. If I'm going from a line value to a phase value, I'm root 3 smaller. I have to make the value smaller. So line values for voltages in Y are always bigger. Phase values are always smaller. And then for current, I phase is equal to I line. Okay, they are the same. All right, so nothing too crazy with that. Just put that up a little bit. So you can pause that and write that down if you haven't already. So secondly, we are going to look at delta now. Just get these rules out here so you are aware of them. And then next video, I'll start adding some math in and expanding on them. So in this one here, we're going to use and look at 120 volts as well. So we're going to look at 120 per phase. And in our delta configuration, the only difference between a Y configuration and a delta configuration, structurally, if you're looking at an alternator, is how the connections are made in the junction box or the pecker head in the top of the motor. A three-phase Y connected alternator or a three-phase delta connected alternator internally looks the exact same. There's nothing different. It's just how these connection points are made on each side, which I'll break down maybe in your lab class when I end up seeing it. So in this one, we have 120 volts, 120 volts, 120 volts. If we go now to look at a voltmeter, if we go to take a voltmeter and we go across this coil, if we go across that coil right now, we're going to read a voltage of 120 volts, right? However, notice that this point here is also connected to that point, so it technically is the same point electrically. This is the same point electrically on this side, which means it's like a Moret joint, right? There's no difference from this point to this point. And if we go from here now into our line values, these points here are the same as these points. There's no difference electrically between them. So if we read 120 volts here, that also means that we're reading 120 volts in the line. So there is some rules that are completely flipped, going from delta to Y. So in delta, our E phase is now equal to E line. They're the exact same. So in a Y configuration, your current is the same in phase and line, but now in delta, your voltage is the same. So the rules flip for voltage and current when you go from delta to Y. Now let's look at the same value, that same 10 amps of current. So we had 12 ohms, 10 amps. So let's look at 10 amps. So this is 10 amps, and this one is 10 amps. And this example could be a motor drawing it or an alternator producing it. The same applies. But if we take an amp clamp and put an amp clamp around this point, we read 10 amps. If we end up putting an amp clamp there, we read 10 amps. If we come out to our terminal values, or where they're connected together, and out to the line, notice now that there's not just one coil that's seeing those 10 amps, there's two of them. So when we come out to the terminal and the line, we're actually looking at the vector sum of those two. And those currents, as we know, are not 180 degrees apart from each other. So it's not just like a regular parallel circuit, single phase parallel circuit, where they would split off, right? One go one way, one go the other way. These are 120 degrees apart from each other. So the same rule that we did before, we now have 10 amps of current. So they are now going to be √3 larger. And we get an answer of 17.3 amps. So I would see 17.3 amps produced phase number 1, phase number 2, and phase number 3. And one thing I will note is that in this class, all three loads, and it can be just assumed in my class, I think Mike will do things the same, but we will always be using balanced loads. We're not going to be using unbalanced loads. I will show you unbalanced loads in lab class and just the effect that it ends up having on the circuit when they're not. But anytime we're doing math, they're going to be balanced loads. That way life is a little easier for you. So a couple things I just want to say. We are going to be doing, I would like to do 4 tests, but depending if we miss any time or whatever, it'll maybe drop back to 3, but typically what I like to do is a delta Y test in around week 3 or 4, depending on how you're taking it, picking up the material. Then I'll go to 3-phase alternators, which is just an extension of this and how they work. And then we go to 3-phase motors. And then after that, we'll finish off a little bit with single-phase motors. So I know a lot of times Theory B is a class that some people have some difficulties with, or don't maybe don't see how they are going to apply that theory to everyday work. I do understand that a lot of times if let's say a motor breaks down, what do you end up doing with it? Well, that motor ends up being taken out and you replace it with a new one. You're not always opening them up and figuring out what's what. But I would say if you do pay a little bit more attention to some of the things, I have found that a lot of guys have found it invaluable to when they do come across a motor and it is burnt out, just to kind of, you know, get a sense of what's actually going on inside, what type of readings they're supposed to be looking at inside. So this can help you out as an electrician, even though you may not think that, well, this stuff, you know, a little bit more so, but when it gets down to the motors, try to get some interest, or maybe come into the class thinking that there are maybe some things you can glean or take from it to apply to your job, because if you come into it with a little better attitude, then you're going to feel a lot better about the course and maybe pick more information out from it. So I try to not go ahead too much unless, you know, guys are comfortable with what we have, or with what we've been through, the material we've been through. But please feel free to, you know, talk to me in lab class, or even email me about things, and I'll talk to you guys on Friday. I believe it's Friday for you guys, as to what material, like if you would like me to print out all the worksheets and give them to you, or if you'd just like me to upload them online. Okay, so that is it for today. I hope you have a good day. Hopefully this wasn't too complicated for you. Oh, one last thing, I will just write this formula. I line is equal to I phase times root 3, and I phase is equal to I line divided by root 3. So that's the formulas for current in delta, and that's the voltage for Y. And I'll just re-summarize those at the start of the next video. Okay, ciao.